Yeah, I'll just quickly share with you some code, and I'll just want you to quickly comment. It's really for your reference. We might need to redo the code from scratch. So first is the rhythm scan that is already deployed and running. It's running well, so we're not making any changes there. That's the one we use for training. So that's just for your reference. You might want to make suggestions as to how we should train differently for the BreastMNIST dataset. But this is just a reference for what worked for us before.
The provided rhythm scan code demonstrates a robust backend training pipeline using Flask, handling data loading, training with Keras, and generating performance visualizations like accuracy loss plots, confusion matrices, and misclassified image displays.
So we are moving away from Flask, eventually just training on the server, but then just using JavaScript for displaying the results of the model, so the performance of the model on a HTML page, and also later on deploying the web-friendly version of the model as well. So users can upload their own images and get results.
For a dataset stored in folders, with the training process and results logged dynamically into structured files for each iteration. For BreastMNIST, the primary difference lies in its compressed .npz file format, requiring a pre-processing step to load and split the data. Since you're moving away from Flask, the training workflow would ideally shift to client-side processing or pre-training offline, with the model converted to TensorFlow.js for browser-based deployment. Visualizations and results logging can replicate Rhythm Scan's outputs, but should be implemented directly in JavaScript to match the new deployment approach. The ConvNet architecture and training settings can be adjusted slightly for the grayscale BreastMNIST images, ensuring compatibility with its dimensions and binary classification task.
So I assume we're using dimensions of the images as they are. I'm not sure. I assume they're consistent. We have to probably check the metadata for the images for dimension, or I'm not sure if we have to check each image individually. How do we figure that out?
Displaying the model's performance on an HTML page sounds like a great way to make the results interactive and user-friendly. You can include performance metrics like accuracy, loss plots, confusion matrices, and selected misclassified examples directly on the page. Deploying a web-friendly version of the model using TensorFlow.js will allow users to upload their own images and get real-time predictions in the browser, making it both accessible and efficient without relying on a backend.
Yeah, so we'll have to change what we are currently doing. So the export images Python code is just exporting 10 examples that just took place on the front page, just for reference. Then we have reviewing the data code. Yeah, I'll share the review data and the output of it as well, just for your reference. And we will, and let me know what next steps are. We're still not writing code, so no code in your response, just continuous text would be great.
The code and output show that the dataset is well structured with clear training, validation, and test splits. Each image is already resized to 224 by 224 pixels, and the labels are consistent across splits. The images have not yet been normalized, as their pixel values range from 0 to 255. Additionally, the label distribution in the training set is imbalanced, with significantly more samples for label 1 than label 0. This imbalance might affect model performance and will likely require techniques such as weighted loss functions or data augmentation to address it. The next steps should include normalizing the pixel values to a range of 0 to 1 to improve the model's convergence during training.
Okay, we're already doing normalization in the code. I haven't shared the training code with you yet. We did test it a couple times. We had some issues with that code. In the original performance, we just did the accuracy. We didn't do area under the curve. We would definitely like to include the areas under the curve.
The dataset is loaded from a .npz file, and the images are normalized to a range of 0 to 1 before being reshaped to include a channel dimension for compatibility with convolutional layers. Class imbalance is addressed using computed class weights, ensuring fair learning across the two categories, benign and malignant. The model is defined as a sequential convolutional neural network with 3 convolutional blocks, followed by fully connected layers with dropout for regularization. The binary cross-entropy loss function and metrics like accuracy and AUC are used to evaluate performance. Data augmentation is implemented with rotations, shifts, zooms, and flips to improve generalization, and training parameters like epochs and batch size are input dynamically, adding flexibility. Callbacks for early stopping and checkpointing ensure the best model is saved during training. After training, the model is evaluated on the test set, and performance metrics, including accuracy and AUC, are reported. The model is saved in both .keras and .h5 formats, and there's an option to convert it to TensorFlow.js for browser deployment. Grad-CAM is included to generate interpretability heat maps, helping visualize which regions of an image influence the model's decision. The script also outputs a classification report and confusion matrix for further evaluation. The next steps involve refining the workflow to ensure all key results, such as accuracy, AUC, confusion matrices, and Grad-CAM heat maps are displayed on an interactive HTML page. The TensorFlow.js conversion prepares the model for deployment, enabling users to upload their own images for predictions. Addressing any training issues, such as hyperparameter optimization or augmentation tweaks, can further improve performance.
Yeah, we're really going into the woods on this dataset. Yeah, before we had the Python thing, Flask. So this thing has a Flask backend, so all the data is stored on my server, and I'm serving it that way. That's with Rhythm Scan. We are now trying to improve it. I'm actually using a different dataset. So this one has this breast scan images. I think they're CT scheme images. Yeah, if you can confirm, I'm pretty sure they are CT. But yeah, they have, some of them are benign, some malignant. We have 3 different folders. So the page, the HTML currently is just showing examples of the 10 images that we exported from the dataset. We might have to export them all, but probably won't display them because it will make the web page too slow, potentially, if you can comment on that. Yeah, we don't want it to be as heavy as this one. This tool is quite heavy as well. The vision impairment simulator is a bit heavy as well. We would like to avoid things like that. I think this is also because it has a Flask backend. We would like to avoid that because I can actually hear my CPU, GPU going when I'm using this. So I'm not sure. It should work on your end as well, but yeah, I think it must be the GPU. Anyway, I'm dealing with different images now, and yeah, we'll have a similar display. Do we need a train test validation? The image I'm attaching, if you can comment on that one, is to do with so someone already did training on this dataset and had some great results with it. So we will essentially try to replicate those results. Yeah, we might split the application into 2, so have a similar interface as a Rhythm Scan to begin with, just to show the performance of the model, and then potentially we'll have another page where you could load your own images. How does that sound? Or would you recommend combining the 2?
The attached table shows benchmark results for different machine learning methods on the BreastMNIST dataset, evaluating both AUC and accuracy metrics. ResNet 18 at 28 by 28 resolution achieves an impressive AUC of 0.901 and an accuracy of 86.3%, which is slightly lower than Google AutoML Vision's AUC of 0.919, but comparable in terms of accuracy. The ResNet 50 models, while performing slightly worse overall, still offer competitive results. AutoML methods like AutoSclern and AutoKeras show solid performance, making them viable alternatives for automating model optimization.